Um, um, we'd then fill it up with charcoal after having started a small fire, and we'd bellow our hearts away for about 4 hours or so, filling it up with charcoal and a bit of ore, and a bit of charcoal and a bit of ore, all from the top, until eventually we'd crack the front door of the furnace off, and we could extract this, an iron bloom of a nice spongy mass of um, iron and slag. Now, what we could do here is we can go, great. Both furnaces have produced an iron bloom. That means both fuels have produced an iron bloom. Great. We can, wipe our hands, go to the pub, call it a good one, and then into things there. Well, we did do all of that. We did collect an awful lot of data, and that actually shows us quite a lot of what's been going on within the furnace, and gives us quite powerful insights, and helps us understand the smelts a lot better. So the types of data that we recovered, well, first and foremost, as you might expect, collected temperature data. We collected temperature data from both the smelts, and so this will tell us if the furnaces were actually getting hot enough to produce lots of iron. And it will allow us to as well compare the performance of the two fuels. Also, we can look at the slags. That's the waste material produced from smelting iron. We can cut it open, and we can look at the microstructures, via metallography. And this will tell us if the atmosphere within the furnace is actually reducing enough to produce lots of iron. Because it's important to remember that smelting iron isn't just about the right temperatures, it's about the right reducing atmospheres within the furnace as well. We can also look at the chemical composition. Because as I say, we want to see if there's a difference between the two sets of material, those produced by the wood charcoal and those produced by the peat charcoal. And again, of course, the furnace material itself, we can look at the chemical composition there and see if either of the furnaces have exhibited particular characteristics based on what fuel they've been exposed to. But if we look at the temperatures first, these are the temperatures recorded from some thermocouples, that is to say, some fancy thermometers, inserted through the tuyere. So what that means is that these thermocouples were placed through the area that we were bellowing into, sort of a little hole into the furnace. That lets the air be forced inwards. And so in theory, this is the hottest part of the furnace, the formation chamber, as it's often called, where the iron actually becomes an iron mass. And we can see that red, denoting the temperatures from the peat melt, it gets up to 1200 degrees, almost 2 hours before the wood charcoal does the same. Unfortunately, we can't track the temperature beyond 1200 because the thermocouples we were using would degrade past that temperature. But nevertheless, we can see a really powerful thermal performance from the peat charcoal compared to the wood charcoal. If we look further up the furnace and actually look at the highest temperatures the highest readings we took at 60 centimeters, they're basically the same. There's this big thermal performance difference isn't really apparent until the last hour or so, where the wood charcoal has sort of a bit of a second wind, which the peat charcoal, it maybe starts to have one, but it's not the same. And I suspect that the reason for this isn't an inability of the peat fuel, but actually a result of blockages within the furnace. When you put your fuel within a furnace, you need to make sure that it's the right sort of size and that the sizing's consistent. Because otherwise, your fuel will burn at different rates when it's within the shaft, which will create pockets of air, big voids, which will suspend charcoal and ore in the shaft until the void is completely burnt out, and everything above that will suddenly come crashing down. And so you might imagine that can impact a nice even spread of temperature up the shaft if the material in it is creating voids and crashing down and so on. But again, it's an easy fix. You cut your fuel smaller and you cut it more regularly. And as blockages were quite a distinct characteristic of the peat fuel smelt, that's all we'd have to do. Just cut the fuel a bit smaller, cut it a bit more consistently, and this shouldn't be an issue. Now, if we were to look at the blooms, I put them in quotation marks because in theory you should really be smelting for a lot more than 4 hours. But this gives us a really good idea of what's going on within the furnace. We can see on the left, we can see sort of homogeneous sort of silvery masses within a much larger slaggy lump, effectively. And so what that's telling us is that we produced a decent amount of iron. If we continued things as they were, we'd probably have just a fair bit of iron. But if we look to the right and have a look at the bloom that was produced by the peat fuel, we're maybe struggling to see the same sort of silvery areas. And when we do, it's quite foil-like. It's very thin and it's more strandy. But what that's telling us is that actually we might consider that smelt a bit of a failure. And so at this point, we might actually ask, well, we've got a bloom, but did the fuel actually work at all during the peat smelt? That's where the metallography comes in. Now, if we just ignore all the black stuff, that's voids, that's irrelevant. But if we look here, we can see that everything within this red circle got a fairlight lath, and everything outside it we can consider sort of a globular wustite. And to cut a long story short, this means that we've got the right temperatures and the right reducing atmosphere to produce lots of iron. And we sort of knew that from the cross section. But if we look here at the peat bloom, things might look pretty different. But actually, these Christmas tree, car parquet, ladder type shapes are also wustite. Just rather than being globular on the left, it's dendritic, simply because it's cooled a lot faster. So that doesn't really mean anything other than, again, we're getting the right sort of temperatures and the right sort of environments to produce iron. And if we look here, this is also fairlight. Rather than being lathy, like it is on the left, it's crystalline. And so, while we've got the right temperatures and the right reducing environments to produce lots of iron, something's altering the chemical equilibrium, the chemical processes to produce lots of iron, like we did with the charcoal fuel. Thinking about it, it's probably the blockages. As you might imagine, if the ore is suspended at one part of the furnace, then crashes down to a much lower part, it's spending a lot less time at certain temperatures and certain environments. And so again, if we just cut that fuel a bit smaller and a bit more regularly, we probably would have wound up with a lot more iron. Talking of iron, all this white stuff here on the right is iron, but we've also got these sort of beige bits sort of affixing to the iron. And I was worried this might be sulfides. Sulfur is bad when it comes to iron. If it's in there in any sort of quantity, you're going to wind up with a metal that's unworkable. It's going to be really brittle, essentially. When it comes to smithing, you're not really going to be able to do an awful lot with it. And unfortunately, when we did the PXRF analysis, the only difference really between the two sets of material was in sulfur. So this sort of confirmed my worst nightmares that even if we were to fix the blockages and have produced lots of iron, the bloom from the peat fuel smelt would still have been very heavily enriched with sulfur, as we can see here. The only way this would have been introduced, of course, is the fuel. But if we ever look at the charcoaling of that fuel, its production, we might expect that this would have driven off a lot of the sulfur. Sulfur turns into a gas at around 444 degrees. So if we draw a dotted line here, you can see that one side of these charcoaling pits that was letting us down. In this instance, it's the right-hand side that's failing to maintain temperatures above this threshold. Now again, we didn't have really any experience in charcoaling heat, and so somebody that's more adept could quite possibly resolve this quite simply. But if we also look at these spikes in temperature, this is associated with fanning the pit. And so if instead of doing these experiments on a golf course somewhere in South Yorkshire, if we did this on sort of, I don't know, a windswept island in the North Atlantic, I wonder where you get those. The natural draft would have quite likely assisted the charcoaler in maintaining temperatures above this sulfur threshold. In addition, of course, to just being more experienced, I doubt this sulfur problem that we had would have been an issue for somebody in the past, um, in the region that we're looking at. I also took the XRF analysis of the furnace material, as I said. Each red dot here is a reading from the back of the furnace, from where the tuyere is, and each yellow dot is from the front of the furnace, where the door is that we cracked open to retrieve the bloom. And unlike the slags and the blooms, this produced quite substantial differences in the chemical composition between the two sets. Most notable here in the sort of 4,000 to 30,000 parts per million range. Titanium, pretty similar, but we've got a slight elevation in phosphorus and chlorine, of sulfur, but also magnesium in the furnace material that's been exposed to the peat fuel. And so with a larger data set to make it more statistically significant, we could create some sort of multivariate statistical model, something like principal components analysis, which will be able to tell us, well, it will be able to create categories. One sort of category for material that was likely exposed to wood charcoal, or one that was likely exposed to peat charcoal, based on some of its principal components. In this case, the elements here. And that's hugely significant because that means we could take a PXRF reading, which is quite a rapid, quite a cheap, quite a simple way of taking readings of the chemical composition of things. We could apply that to furnace material that's in museums or that's actually still out in the field. And we could then apply that using the statistical model and figure out what types of fuels furnaces were being exposed to in the past. And so to look back on the aims, the experimentation and the metallography can suggest that peat charcoal could work as an iron smelting fuel. There's a few problems, like I said, but problems that shouldn't be easy to iron out, if you pardon the pun. Yeah, I hate myself for that one too. And the substantial elemental differences in the furnace material should help us identify what type of fuel is being used when we reassess the archaeological record. Now, this has wider implications than just telling what type of fuel is being used, you know. This goes beyond simple resource management. Of course, if peat is being used, then we know that communities are valuing increased economic viability, potentially. But they're also strengthening a cosmological or an ideological link of metalworking to watery places. For example, we know we've got metal artifacts in rivers and lakes, but also quite a substantial part of Scotland is using what's called a bog ore as their iron ore. And as you might imagine, that also comes from relatively damp and watery places. In fact, probably places quite similar to where the peat would be coming from. And so certain theoretical frameworks would call this a content bias. It just makes sense to be using peat. But If they're not, if it's dead wood charcoal, then it would seem that communities are endangering marginal woodland resources. Um, and the only reason I can think of for this would be some sort of enhanced status, some sort of ritual of conspicuous consumption. Um, for example, maybe the metal worker, maybe the artifact itself, the metal work, or maybe the client needed their status to be reaffirmed at sort of every stage of the creation of an item. And perhaps using wood charcoal would have been a way to do that. Now, it's important to note here as well, peat was being used quite widely domestically. And as anyone that's burnt peat can tell you, it smells quite substantially different from burning wood or burning a wood charcoal. And so if you were a metal worker and you were stood around a wood charcoal pit, and then you were stood around a smelting furnace or a smithing hearth, all day working away on your craft using a wood charcoal, you would smell substantially different from the rest of the community. And let me tell you, that smell does not come out easy. Um, that sort of barbecue smell lingers on you, in your skin, your hair, and your clothes for days on end. And it doesn't matter how much modern scented soap you use. And so I suspect that you'd be able to tell you were within the presence of a metal worker quite quickly, even with your eyes shut. You'd probably be able to do that for quite some time after they'd actually finished practicing their craft as well. So this might have some really powerful implications for the idea of the social inclusion and the social exclusion of metal workers from various points in time within the community, as certain ethnographic accounts might attest to. So as we can tell, there's a lot more research that needs to be done here, and I've been doing some of that. I spent 2 weeks down at the Wolfson Laboratories at UCL, doing a lot of scientific work on this. Done some scanning electron microscopy with energy dispersive spectrometry, the SEM EDS. And this gives us a better insight into the chemical makeup of the slags and the ores. It's a lot more precise than the PXRF. You can highlight an area, a micron wide, and it can tell you what the chemical composition is of that specific area. We've also prepared some samples for laser ablation inductively coupled plasma mass spectrometry, which I do implore you all to try and say 10 times fast after after this meeting. But this again, it's another way of looking at the chemical composition of the slags and the furnace materials. But it's even more precise, and it can look at trace elements, which can help us then produce what's called a mass balance, which is a very painful spreadsheet, which can tell you the efficiency of certain processes. And again, it gives you a better idea of exactly what the ratio of X amount of fuel is to say Y amount of ore to produce Z amount of fuel. And of course, the PhD that I mentioned earlier, I'm hoping to see if there's any identifiable regional or cultural traditions within iron smelting throughout northern Scotland around the first millennia AD. And I strongly suspect the use of peat might be quite a strong signature in this project. But for now, until I get funding, that's unfortunately where I'm going to have to leave things for now. Now, a lot of people contributed, a lot of blood, sweat, and tears to this project, including myself, of course. And I had a lot of interesting conversations with people. So I might just leave this up, if that's okay, for people to read in their own time. Well, I take any questions people might have. Thank you for listening.
Paul, thank you very much for that intriguing and informative talk. it is detailed. It's also dense as well. So, as a non-metallurgist and non-technical person, I feel like going and lying down in a darkened room. But the data you've provided with us with is absolutely fascinating. Can I invite questions? And it might be best, folks, if you put them in via the chat, and Paul can pick them up from there. And I can also be monitoring them, and we can see what's exercising our audience today, Paul. Can I just kick off with one, Paul? And I appreciate the detailed technological aspects, the metallurgical and furnace making aspects of it, but I was very interested in the challenges you've set yourself for the PhD, and I'm very conscious that might well be work that's lying in the future. Is there much evidence just now in the literature, Paul, of that type of work going on with peat in the past rather than charcoal?
So you're asking if there's already been research like this, sort of in general, do you mean? Or
just wondering, Paul, if there's evidence of that use of peat that you've been
gotcha.
evincing as being possible. Sorry.
Yeah, no. Yeah, so other than, of course, the depositional relationships I mentioned earlier, at the how they struggled to differentiate between lenses of charred peat and charred charcoal, or charred wood, sorry. And it's not really been something that anybody's looked out for, to be totally honest. I've taken some samples of the charcoal, and I've popped them underneath the microscope. And while most of it looks meaningless, of course, because it's made of plant matter, there's still roots and stuff that survive, and they still leave a slight trace. And so really, I suppose it depends just how aware of peat charcoal you are. So of course, they weren't thinking about that at the how, and that's potentially why they struggled to differentiate between what is potentially charred peat and what is actually charcoal. But yeah, currently it's mostly this sort of depositional relationship. That's sort of the canary in the coal mine sort of thing. I hope that was along the right sort of lines as you were hoping for there.
It was indeed, Paul. Thank you for that. Mickey Van Litz asking whether you see a distinct difference in effort and labour intensity between charcoal or peat. Question that's come up in the chat.
In terms of producing it, not really. It's the same sort of process. It's actually quite labour in unintensive. It's you mostly just set the fire and watch it. Of course, we had to fan it, and then things got distinctly unpleasant. And I'm sure, and myself and my volunteers have developed several kinds of ancient medieval disease or whatever for lungs. Or bones might look interesting to assess in the future. But yeah, no, it's not a difficult task really. It's not something to worry about. But in terms of harvesting, that's maybe an interesting point. Because of course, if you're using wood, you're having to restrict yourself to coppice cycles. You're having to wait, okay, right, we've got another 25 years before we can harvest from that woodland, for example. But with peat, you've got to be careful because you don't want to overcut your peat because you can run out of peat. But you're not restricted to that. Oh, well, we can't harvest any of that material for the next generation or so. So it's less intensive in that regard.
Okay, thank you for that, Paul. Any other questions? I'm not seeing any more coming up in the chat.
That either means I've done a good job at explaining things, or I've thoroughly put everyone to sleep, I think.
Absolutely not, Paul. Absolutely not. I think it's been a fascinating talk, and it's interesting to see the experimental platform that you've laid down that will presumably give you the basis for going on to the more open field work that would come from your PhD subjects. I think it was fascinating, and I see chat coming up saying that as well. Very interesting. Paul, thank you very much for your contribution. I know you need to be somewhere else quite quickly, so happy to thank you again for your work, to wish you well in your future studies, not least in securing funding to carry on this work in a PhD, and thank you. I'm sure we'll be hearing more from you in the future.
Fingers crossed, and thank you.
Thanks, Paul. Okay, folks, our next speaker is Ellie Graham. Ellie's going to be kicking off at just about 12 o'clock. I think we'll maybe bring it a little bit forward, Ellie, if you're happy to do that. I know you've been with us for the first talk. So what I suggest, folks, is we take let's take a 10-minute break and come back at 5 to 1, and I'll ask Ellie to give her piece then, which is entitled A Slice Through Time, a trio of eroding Shetland broths. Ellie, it sounds like a delectable feast that you're preparing for us for that. A very interesting recipe, and we look forward to hearing that. So folks, stay online, stay on Zoom, and let's take a 10-minute break, and we'll start off at about 5 to 12. Thank you very much. See you in 10 minutes.